This is a question to the engineers and physicists here. Calculate something, of course, but what? What is the word that comes to mind? Kirchhoff's laws, exactly. Because, as every electrical engineer or physicist knows, Kirchhoff's laws are the laws that describe how currents distribute themselves in circuits. And you have been pre-programmed. If you see a drawing that has wiggly lines in it, like this, it's a Kirchhoff's law problem. Have you ever seen a real circuit that looks like that, by the way? I haven't. So here we are, 500 milliseconds into the exam, and you already know problem number 5 is a Kirchhoff's law problem. You have not yet read anything. Simply by virtue of that figure and knowing that those kinds of problems get solved with Kirchhoff's laws, you've already made that identification. Once you've made that identification, how much physics is left? I see a lot of people shake. No, there's nothing, right? Because it's just a matter of taking those numbers, which are nicely presented, put them in Kirchhoff's law, turning the crank, and a few minutes later, you have the answer. Do the students understand Kirchhoff's laws? No, because if they understood Kirchhoff's laws, they would have had no problem with this problem. So can we blame the students for that? I don't think so. Because open any physics textbook, or any chemistry book, or engineering, or mathematics book, whatever, and somewhere on page 20, there's this box that says problem-solving strategy. I'm sure you've seen those, right? Read the problem, make a sketch. You know, it's just a prescription for how to solve problems. Now imagine you're a student, you want to go to Johns Hopkins Medical School, you've heard nothing but horror stories about physics, and you see this box, problem-solving strategy. Wow, my key to success. You take out your yellow highlighter and you highlight the entire section. It's not really necessary because the publisher has already highlighted it, but you highlight it anyway. And you memorize the approach. Now comes the first homework. Here's the strategy, there's the problem. And you apply the strategy to the problem, and it works. Why does it work? It works because the textbook problems are designed to match the strategy. And you think, yes, I'm going to get into Johns Hopkins Medical School. Maybe physics is not that bad after all. And now you apply it to problem number 2. And it works again at problem number 3. Remember that I told you that some students said that physics was boring? I could never understand why people would think of physics as being boring. But if it's just applying recipes that you don't even know why they work, it is boring. Not only is it boring, it's frustrating too. Because now comes problem number 4. Here's problem number 4, here's strategy. You try, and it doesn't work. Because as we all know, there are no strategies for solving real problems and all problems. So here you are, in this class, you've been fooled to believe that there is a recipe-based, rote approach to solving problems, and you discover that it only works 75% of the time. What kind of professor is this who gives me a strategy that only works 75% of the time? It should work 100% of the time. So you get frustrated. So frustration, boredom, is very likely to occur for 40% of students in my class at Harvard. So that's when I finally asked myself the question, what should I do? And the first thing that came to mind was, well, maybe I should only teach graduate courses. But I wasn't willing to give up that quickly. And it turns out that the solution presented itself completely serendipitously. Remember I told you that I was afraid that the students would be offended by the simplicity of the FCI. Well, they were not offended at all. They were very worried because they realized that there was something wrong. They had this midterm examination coming up, and they were worried that they were not going to do that well. So what did they do? They asked me to have a special session to go through every single problem on the FCI. So I booked a large classroom at night, and we went through every question of the FCI. When we got to the question of the heavy truck and the light car, I made a sketch of the car on one side of the board, of the truck on the other. I drew the forces, and then at the end I said the force of the truck on the car and the car on the truck are equal to each other in magnitude because of Newton's third law. What more is there to explain about it, right? I turned around, and I could at once see from their faces that they were confused. So I said, does anybody have a question? They were so confused they couldn't articulate a question. You know how it is, right? If you're really unsure about your own knowledge, it's hard to say, I don't understand this or that. I knew this was serious, so I thought, you know, I better spend some more time. So I erased the board. I did everything from the start again, but this time I brought in acceleration. I said, even though the forces are the same, the effects are different because the truck is heavy and the car is light. I mean, I gave what I thought was the most brilliant explanation you could give. And at the end, I triumphantly turned around, only to see that they looked even more confused. And they were still not able to articulate a question. So in a moment of despair, I did something I had never done in my class. I said, why don't you discuss it with each other? And something happened that was just amazing. The whole classroom erupted in chaos. They all started arguing. Forgot about me in front of the classroom. I could have walked away, they wouldn't even have noticed it. And what happened was that in just 2 minutes, they figured it out. At first, I couldn't understand it. But imagine you have two students sitting next to each other. Mary, who has the right answer because she understands it, and John, who still has the wrong answer. Mary is more likely to convince John than the other way around, simply by the force of logic, on average, right? But this is important. Mary is more likely to convince John than Professor Mazur in front of the class, because she has only recently learned it. She still knows what the conceptual difficulties are that a beginning learner has. She still knows what is going on in John's head. Whereas Professor Mazur learned it such a long time ago. To him it is so clear that he cannot understand why a student is struggling with it. I'm actually making a kind of strange argument here, right? Because we tend to think the more you advance in your own discipline, the more qualified you are to teach it. I'm making the opposite argument. I'm saying that the more you advance in your own discipline, the harder it becomes to connect to a beginning learner. As you clarify your own thinking, you forget how you learned it. You forget your own struggles. And I'm sure you've had it as a teacher, that a student comes to you after your class and says, Professor, I don't understand, blah, 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 blah. And you look at the student and you think, what's wrong with this student? What is there to understand about blah, blah? So it's clear, right? Because you no longer think like that. You don't know what the stumbling blocks are. So when I saw that, I thought, wow, maybe there's a way that I can exploit that in the classroom. Let's go back and think about education. Let's think of education as a two-step process. Step one, transfer of information. Step two, assimilating that information. Which is the hardest of those two parts? I think we all agree it's the second part, right? Yet, where did that assimilation take place for you and for me? Where were the moments that you saw, oh, now it makes sense? Did that happen while you were sitting in the classroom listening to your teachers? No, it happened outside of the classroom. But given that it's the hardest part, shouldn't we put that in the classroom and throw the information out? I mean, most of education puts all the emphasis on step one, the transfer of information, and then hopes that step two occurs somewhere on its own outside of the classroom. If you think about it pragmatically, it makes no sense. We should really invert that sequence. We should do the information transfer outside of the classroom, and in the classroom, when we're face-to-face with the students, focus the attention on the sense-making, on the assimilation, on the practice. So that's basically what I started doing in my classroom. I now no longer transfer information. I give students the responsibility of gathering the information before they come to class. So the homework comes not after class, but before the class. And then in class, I help them assimilate that information. I don't expect them to come to class knowing everything. That'd be really nice, but then I'd be in trouble because I wouldn't be necessary. So there's pre-class reading. It doesn't have to be reading, right? I can also ask them to watch a video of a lecture before coming to my class. And there's an assignment to actually force them to do it. And then in class, I don't try to cover everything, right? Before that, I covered everything and nothing was learned. So what's the purpose of coverage anyway? And I do that by asking questions. So I'll talk a few minutes, and then I'll put on the screen a question, which I call a concept test. I give the students a minute or two to think about it individually and formulate an answer. Then they provide a response with the clickers, or another system. It doesn't have to be the clickers. And then I tell them, now try to find a neighbor who has a different answer and try to convince that neighbor. It's important to say that they have to find a neighbor who has a different answer. They'll very happily talk to somebody who has the same answer, but then you don't learn anything, right? So if they turn right and the person has the same answer, you say thank you very much, and you turn left, right? You go around until you find somebody who has a different answer. You will have to do the same thing in a minute. And then that's where the learning takes place. And then I have them answer it again, and then an explanation. Let me show you a little video clip from my classroom. So we have a rectangular loop that is placed in a uniform magnetic field in the direction indicated by these arrows. So the question is, what are the magnetic forces on the 4 different sides of this loop? So take a minute to think about this, and then enter your answers. Don't worry about the question. I don't want them to talk to each other. They don't see this distribution. It's on my screen. We have a disagreement clearly here. So I tell them there's a disagreement, but don't show them what the disagreement is. We can convince one another of the correct choice. Initially, we had sort of an even split, and now we have an absolutely overwhelming majority for choice number 2. So in reality, it's a little bit longer than this, but you get the idea. You saw the sort of the engagement and the chaos. So the flow chart for a real lecture is more or less like this, and I realize the letters are too small for you to read, but I'll tell what's there. And you can download my slides after this talk. So I start with a brief presentation, and then I'll talk maybe 5 minutes or so, not more. And then I ask one of these questions. I poll them. If more than 70% gets it correct, I don't ask them to talk to each other, because they'll basically say, oh, I got the same answer, and they'll start talking about something else, right? So the question was basically too easy. So I explain, and then I repeat the process from the start with a more difficult question. If between 30 and 70% gets it correct, that's perfect. Then I ask them to turn to each other, teach each other, and I poll again. If less than 30% gets it correct, it doesn't make much sense to have them talk to each other, because there are simply not enough students who have the right answer, right? It's too hard, the question. And basically, I revisit the concept and repeat with a harder question. The ideal pathway is that one. And as you saw in that little video, there's sort of two things that are important. One is it's active, not passive. The students are in the class practicing their knowledge, in a sense. You can't sleep through class, because every few minutes your neighbor will start talking to you. The other thing is it's a two-way flow of information. It's not just me delivering information to the students. There's information coming back. I know whether they understand it or not, right then and there. Normally you have to wait till an exam to find out if your students have gotten something or not. What's more, students get to assess their own knowledge continuously. Imagine you saw that second distribution, right, where almost everybody had B, which is the correct choice, and a few had A. Well, if you're in A and you see that most of your classmates got B, you go, wow, I better look at this. So you have an opportunity of assessing yourself continuously. Do you want to try it out? Are you ready to try it out? Did you all do your reading? I asked to read about thermal expansion before coming to this. No? I'm just joking. But you know what that means. That means I have to lecture you. Actually, I'm very grateful to you, because the one thing I miss about my previous approach to teaching after I switched to peer instruction was that I don't get to lecture anymore. And I love lecturing, so I'm happy that you give me an opportunity to lecture you. So I'm going to talk very briefly about thermal expansion. Right? Materials get bigger, expand when they get hotter, and this is very pronounced for metals. And it's a very important thing in engineering, right? If you've ever been sitting in a train, you've heard that the wheels go clickety-clack as they go over gaps that are between different segments of the rails. And you may have wondered, why don't they put the rail against one another so you don't have the clickety-clack sound? Well, if they were to put the segments of the rail right against one another, there would be no room for expansion in the lengthwise, and if the metal would get hotter, it'll buckle and the train would derail. The same is true for steel frame buildings and so on. Now, the reasons metals expand is that as they get hotter, the atoms get further away from one another. So this is a cold metal, and this is a hot metal. Cold, hot. All of them get further away from one another. Not just the 9 that I showed them, but all of them, okay? Why is it they get further away from one another? This is not important for my question, but I'll tell you anyway. It's because atoms don't sit still, they shake. And the amount of shaking is proportional to what we call temperature. What we perceive as temperature is basically the motion of atoms. So when you put your hand on something, you are basically feeling the vibrations of the atoms. Not directly, but indirectly. So this is a hot atom, and this is a cold atom. Now imagine you're all atoms. You wouldn't be sitting there still. You'd actually be shaking like this, right? Now imagine your neighbor starts shaking much more violently. You'd go away from your neighbor, right? Atoms are like that too. That's all there is. Questions, anybody? Questions? I knew I'm giving very clear lectures, so. But still, if you don't ask questions, I'm going to ask a question. This is your last chance. See, and what I'm not going to do is, one of the things I could do is I could blank out the screen here, and I could put the question, when metals get hotter, the atoms, 1, get further away from one another, 2, stay where they are, 3, get closer together. But that's not what I'm going to ask, because that would just be me giving you information and you giving me information back. I'm going to see if you can take this concept of atoms getting further away from one another, all of them, and apply it in a different context. So you better understand it. No questions? Wow. So let's go for the question then, last chance. Okay. Consider a rectangular metal plate with a circular hole in it. Now imagine we heat up this plate uniformly so it gets hotter everywhere. What is going to happen to the diameter of that hole? Will the hole increase? Shh, no talking to your neighbor. Individual thinking. Just think in silence. Is the hole going to get larger? Is it going to stay the same? Is it going to shrink in size? And I want you to not jump to conclusion here. Think about it in the context of the atoms getting further away from one another. And then how would you convince your neighbor that your answer is right? So if you're not talking to your neighbor, I'm going to come and talk to you. Good. You've got to talk to your neighbor. And if you've convinced your neighbor, find somebody else, okay? All right. You too?
Yeah.
Okay. If you, okay, good. Do you have an answer yet?
Yeah, I have an answer.
Have you convinced somebody?
Sorry?
Have you convinced somebody of your answer?
And we happen to have the same answer. So I'm listening to
Oh, okay. Okay, good, 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 good. Okay. Well, look at the engagement. I mean, probably by now, many of you have completely forgotten that I'm not here to teach you about thermal expansion. I'm here to talk about pedagogy. I have opened the polling again, so I want you to indicate what you now believe to be the correct answer. If you've not changed your mind, you click the same button you clicked last time. If you have changed your mind, you do change it. So please enter what you now believe to be the correct answer, even if you have not changed your mind. And look at how the conversations are continuing. You got all fired up. You know, it doesn't even matter what the answer is to this question, because I'm not here to teach you about physics. But I'm sure that you will not let me leave this room alive without telling you what the answer is. You want to know what the right answer is. Right? Whereas if I had just given a lecture and I would have said, well, you know, when metals heat up, atoms get further away from one another, and you would have taken notes, and then said, if you take a rectangular metal hole with a circular plate with a circular hole in it, and you heat up this plate, the diameter of the hole will, I want to keep you in suspense a little bit longer here. You would have just taken a note. It would not have been as mentally engaging, right? But now it is. Okay, has everybody answered it? Now, unfortunately, I have some bad news for you, because my brilliant lecture was not that brilliant after all. Only 29% of you got the right answer. Now remember, 29% is less than 30. And I said that if it's less than 30, it's not worth having people talk to one another. It means that basically, of each group of 4 people, only 1 had the right answer. And the wrong answer dominated. So, you know, usually it doesn't work that well, but it doesn't matter. I've made 2 points already today. One is a lecture, even if it seems completely clear, is not necessarily clear. You see, lecture creates a false sense of security. You listen, and often you're not aware that what's being said is different from what your brain is thinking. And you walk away from the lecture thinking, oh, that was all clear. I asked you, I think, at least 3 or 4 times whether you had any questions. Nobody had a question. Right? But when confronted with a situation that's a little bit different, you can't take it and transfer the context. So let's see what the distribution is now. And indeed, it did not improve. We actually went the wrong way, because the correct answer is answer number 1. I can see some people say, yes, I got 1. Now, I don't want you to lose sleep tonight and lie in bed and think, why is it number 1? But imagine you're wearing a metal ring. Imagine you're wearing a metal ring and you can't get the ring off. Do you run it under cold water or under hot water? Hot water, because then the ring expands and the hole in the ring gets larger. You knew it. Or imagine you have a jar of marmalade or something else in the refrigerator. You can't get the lid off. What do? You run the metal lid of this glass jar under hot water, because the metal expands. Or imagine, you'd say, well, that's not fair, because the metal lid has metal at the top and that pushes things out. Well, imagine we have a metal plate without a hole in it. We take a pen and we draw a circle. Now we heat this plate. What happens to the diameter of the hole? It's getting larger, right? The whole plate gets larger, so the circle gets larger too. You say, well, that's not fair. There's metal, there's no hole. If there was a hole, the metal would expand into the hole. But think about it this way. Remember, and I told you this, all of the atoms need to get further away from one another. Let's see if that will be the case. Imagine that we look just at the atoms. This should be gray. The projection is kind of bright. But these are the atoms at the edge of the hole. So this is the plate, this is the hole. Imagine we go outside and we form this big circle. Each of us is an atom, right? And now we step all inwards toward the center of the hole. What happens to the distance between us? It gets smaller. We get closer together. We can't get closer together because our neighbor is shaking more violently. The only way to increase the distance between us is to step outwards and make the circle larger. You won't forget this. But it doesn't matter whether or not you won't forget this because we're really talking about pedagogy. And I think I made two important points. One is your level of engagement is much larger than it would have been in a straight lecture, right? And secondly, what appears to be a completely clear lecture is not that effective, right? You were not able to take that context, and that concept of the atoms getting further away and transfer it to a new context. Okay, in the last few minutes, is this any good? Well, how would you assess whether this is any good? Well, one of the things we can do is we can try the FCI again. And I'm going to show you the data I obtained the very first year I implemented peer instruction. Now, physicists and scientists often will show data, and they'll show these are some typical data. I have learned in my career as a scientist that the word typical is a code word. It means these are the best data I've ever obtained in my entire career. Well, I'm not going to show you the best data. I'm actually going to show you what turns out to be the worst data, because the first year that I did it, I wasn't able to find the right questions at the right level. Just like this question about the hole in the plate was too hard, right? It would have been better if I had a slightly easier question where you would have started with probably 50% of the people was the correct answer, and then it would have gone from 50 to probably 80 or even 90% correct. So that first year I did it in my class at Harvard, I did not have the right questions either. So here's the pretest. This is 1991, first year that I used peer instruction. This is the FCI pretest on the first day of class. And the distribution is not very different because Harvard admits the same type of students every year. Ready for the post-test? Here it is. Yes, there still are some students who are Aristotelian thinkers. We've certainly gotten rid of the gorillas this time. And the improvement is at least twice as large as what it was before. And in fact, in the year since, I've tripled that, simply by asking better questions in class. So what does that mean? It means that the mental engagement helps students address the conceptual difficulties that they have in class. But what about problem solving? I mean, what about textbook problems, right? Not just the FCI. After all, the FCI deals only with force, and force is something you do all the way at the beginning of the class. What about everything else? Well, how do you test that? I knew of only one thing, and that was to repeat an exam. I kept meticulous data, and I was able to reconstruct this histogram of data of an exam I'd given in 1985. And as you see, the average was around 60-something, 62, I think. Some students failed the course, others did extremely well. As I looked over that old exam, I said to myself, and I had never, ever repeated a single question on an exam. Students don't have access to more than a few years of old exams. But even if a student had somehow had access to all of my exams, he or she would have very quickly concluded Professor Mazur never repeats an exam problem. But I was a little bit worried by doing this because in 1985, my class was relatively small. We had about 100 students instead of 250. And I spent a lot of time in class doing sample problem solving. In 1991, I decided not to do any problem solving in class. Think about it. If you want to learn to play the piano, do you go to the concert hall to listen to Murray Pariah play the piano? No. Well, maybe you go, but that's not how you learn to play the piano. You have to play the piano. If you want to train for a marathon, you don't sit in front of the TV eating popcorn watching DVDs of marathon runners. You got to do the running. If you want to learn physics problem solving, you don't sit in your chair watching a Harvard professor solve problems. You got to do the problem solving. In fact, we all reached that conclusion early in my talk. You got to practice. So I still had problem solving, but I'd eliminated all problem solving in the class. So I said to myself, as long as the average stays roughly where it was before, I'm happy because I know they understand the basics better. But you know what? The students actually did better. Statistically significantly better. Here are the two distributions on top of one another. The scores went up by 10%, which is very significant. So what does that mean? That means that better understanding leads to better problem solving. In hindsight, isn't that just obvious, right? But, and I think this is the most important message I really want to leave with you today. If you take that statement and you invert it, you get something that is not necessarily true. Good problem solving doesn't always indicate understanding. I had been fooling myself into believing that I was a good teacher based on my students' textbook problem solving. Remember that example I gave with the Kirchhoff's law, the textbook problem on circuits and the light bulbs? Right? If I'd gone by the textbook problem, I would have thought my students understand everything. But the light bulb problem clearly showed that they didn't. Or at least 40% of them didn't. So I want to give you the URL for the website where you can download these slides and find much other information. You don't need to write that down. Just remember my name, M-A-Z-U-R. Go to Google and then hit this I'm feeling lucky button. And then one more click and you'll have a copy of this presentation. And if you're interested already using p-instruction, there's another resource that you might find interesting, which is pinstruction.net. Thank you so much for your attention.